Come on in, everyone. Feel free to ask me questions. We got about 3 or 4 minutes for class starts, and it's only you two in here. So feel free. All right. Got about 1 more minute left, but feel free to ask me questions before class starts. Got 4 of you in here now. Of course, as soon as I said that, we get a fifth. I can take a picture of that. Save this for my roll. It's like on my roll sheet. It's around here somewhere. Ah, darn it, got another one. Yep, there we go. Got another person there. Drop it. Another person coming in now. Jeez. Who's coming in now? This. Delete that. Oh, yep, we got another one. Yay. I think we actually have our full class now. That's not good either. Got another one now. Oh my gosh, it's a ton of people coming. Yay. All right, looks like we got 7 of us in here now. That's good. I'm going to take one more screenshot, crop it, and save it. And we should be good to go. Save, replace that one. All right, we're good. So before we start, does anyone have any questions? We, of course, still have until tomorrow night, 11:59 p.m. to finish your face-to-face test. If you've already taken it, then it's important that you not ask questions about it yet, because I still have some people that haven't taken it. That being said, if you haven't taken it, and are curious about, some questions you have on, for instance, any of the practice tests, now is the time that you can ask that. So feel free to do so. That's what I'm opening the floor up for. So does anyone have any questions? 25 and 26 homework be pushed back since we, oh yeah, absolutely. Yeah, and remember, those dates just come up automatically. So when we haven't covered something, it's definitely not due. Okay. If and until I cover it, it's not due at all. So never worry about that. But yeah, we do have chapter 25 and 26, which already were set. So I'll definitely be moving that. Today we're going to finish out chapter 24 and jump into hopefully a little bit of 25, but at bare minimum, we're going to get 24 finished. So I think I saw something that I need a mirror behind me to show my hands, but I don't have a handheld one that I can use. Can I use my laptop and angle the camera, then do the test on my PC? Yes, and in fact, you're not even required to have a mirror. It's just a mirror is less likely to allow you to be in such a position where I'd ask you to retake it. So all I'm really trying to do is there's been some students that were possibly a little less than honest that had like stuff in their lap, or in some cases had people behind their monitor or things behind their monitor. So that's what I'm looking for. Is ideally you'd have like the computer monitor, let's pretend this is a computer monitor, sitting like this at some kind of 45-degree angle to me, and then the camera or the mirror over here, assuming the computer monitor actually has the camera mounted at the top of it, then this camera sees this mirror over here. And because of that, I can then see your workspace right in front of the computer. And I can see if you're actually got anything in your lap, or if you're staring at the lap for a long time, or if you're staring behind the screen for a long time. I can see all that. That's the main reason that that's there. So yes, that would be fine. But like I said, you don't have to have a mirror. It would help a lot. You can also, if you want to come to my class, I'll be having a lab at 12:15 tomorrow. Well, 12:45 is the time it starts, but you can start as early as 12:15. And you can't start much terribly later than that. You'd have to start probably at least by 1 o'clock. Let me see. No, 1:30 is about the latest you could start, but you can come to my lab on campus to get that as well. That would be me proctoring it as well. And you can also make appointment at the testing center. They normally ask you to do a day in advance, so you should make your appointment today or tonight for tomorrow, because tomorrow is the deadline. If we end up having some kind of problems, I might be able to push the deadline back a little bit to make it like Thursday if someone just doesn't get it done. But generally, we shouldn't need to do that. I've given you a lot of time, so let me know. So it looks like no one has any questions on any of the practice test type stuff. So I'm going to get right back to chapter 24. When we last worked, I had shown you and derived for you so that you'd understand sort of what happens physically when you connect a capacitor to a battery. So I had worked out the formula for the equivalent capacitance for a series of capacitors in series. That turned out to be 1 over C equivalent in series is equal to 1 over C1 plus 1 over C2 plus 1 over C3 plus dot, dot, dot for however many you have. And then if they're in parallel, we found a neat formula that was a lot easier, and that was C equivalent parallel is equal to C1 plus C2 plus C3 plus dot, dot, dot. So you'll notice from your labs, you'd already learned that resistances add when they're in series, so that R equivalent in series is equal to R1 plus R2 plus R3 dot, dot, dot. And in parallel, it's 1 over R equivalent in parallel is equal to 1 over R1 plus 1 over R2 plus dot, dot, dot. So you see the formulas are exactly the opposite for the resistance. So that always helped me when I find something exactly the opposite or exactly the same, then I can always use that as a mnemonic to help me remember exactly what the formulas are. So you probably already had the formulas memorized just from using them with regards to resistance. Now you just remember it's the opposite for for capacitors. Okay. We also had taken and converted one bank of capacitors. We'd had like a battery that ran to a capacitor, and then that line broke up into two capacitors in series and one capacitor in parallel with those two. And then after that, the wires came together again, and there was another capacitance. I worked out the equivalent capacitance of that. And then bit by bit, I used the different stages that I had used in calculating the equivalent capacitance. I use that to calculate the voltage and the charge on each of those capacitors. So that's something that's challenging, but it's fun, and it's kind of a nice, easy physics problem that requires a little thought. So it's not completely easy, but the main thing is that's something you should be able to do. So make sure you guys can do that. Now I'm going to move on to another example, which is it's not that physically helpful, in that I've never actually seen instance where this particular configuration would be helpful in making something, but it is extremely helpful in further understanding exactly how capacitances behave. So I'm going to get started with that. My charge or on my iPad is not very high, so I've got it plugged in right now, but it's only at like 67%, so that's not super helpful. Uh, so let's go ahead and do my share screen. Again, anybody have any questions while we're opening this up and sharing it? Questions on anything? Okay, so this is the problem that we're working. I still haven't seen anybody suggest adding questions, so I'm just moving on. I now have the chat window open as well, so if you guys need to type something, I will probably see it. Maybe not immediately, but I will see it. So what I have here is example one. It says two capacitors, C1 equals 2 microfarads. C1 equals 2 microfarads and C2 equals 6 microfarads are connected in parallel with one another, and a V equals 24.0 volt battery, see figure. So you can see down at the bottom that basically I have a 24 volt battery at the very bottom, and then the wire runs up, it splits off to a line to go to C1, and then the other line goes to C2. And what I'm saying is capital Q1 and capital Q2 are the charges on C1 and C2 respectively. What I'm going to do is imagine those two being brought up to a full charge so that their voltages are both 24 volts. And then I'm going to disconnect it. It says after they are fully charged, they are carefully disconnected uh, from the battery and each other. Then the capacitors are reconnected in parallel to one another, but with the positive side of C1 is connected to the negative side of C2. What I'm asking in part A is what are Q1 and Q2? That's the charge before I disconnect them, but after they're fully charged with the 24 volt battery. Part B is after they are reconnected, what are charges lowercase q1, lowercase q2, and V prime? And you can see in that last diagram that V prime is the voltage across C2, but though it doesn't necessarily 100% look like C1 and C2 in that last diagram are in parallel, what can tell you they are is the fact that the wire going from the top of C1 to the top of C2, if there was any kind of current flowing, there would be almost zero drop in voltage from the top of C1 to the top of C2. So that means those two are at the same voltage. And then there'd be almost zero drop from the bottom of C1 to the bottom of C2. So those two are at the same voltage. Because of that, you see that the voltage across them are the same, and therefore they must be parallel. Okay, so hopefully that helps you. And I drew it basically showing you that we'd have a multimeter set on DC voltage. That's what the little V with the bar over it and the little dots between the bar and the V. And I've got the black terminal connected to the negative side of Q2 and the red terminal connected to the positive side of C2. So what we're going to do is we're going to make use of our formulas. So here's our solution. What I'm making use of is the fact that C is equal to Q over V. So that means Q is equal to CV, like that. So we can do part A. I'm going to say Q1 is equal to C1 times V. And of course, C1 is 2.00 microfarad. Notice I always try to use 3 sig figs. So that's why it's 2.00. And then that is times 24.0 volts, because that's what size the battery is. I didn't write that down here, but I will now. Okay. So you can see that 24 times 2 is 48. So that's going to give me 48.0. Notice how I completely ignored the fact that there was a micro there. And I'm just going to write the micro again. And a farad times a volt is, in fact, just a coulomb. So we get 48.0 microcoulombs for Q1. So that's one answer. And then Q2 is equal to C2 times V. And C2, I distinctly made it specifically 3 times as big as C1, mainly so you can easily tell how the charges are related, because they're whole numbers and they're differ by a whole number. If you see the charges differ by a whole number, that might tell you something about how capacitances behave. So in this case, it's 6.00 microfarads times 24.0 volts. And of course, 6 times 24, 6 times 20 is 120. And 6 times 4 is 24. So that's 144.0. And the 0 in this case is a non-significant figure, but it still comes out with the micro and the coulomb. And that's Q2. So if you'll notice, the capacitance C2 was 3 times the capacitance of C1, meaning literally if you multiply 3 times the capacitance of C1, you get C2. So notice C1 is 2.00. If I multiply that by 3, I get 6. Now notice what happens if I multiply 48 by 3. If I multiply 40 by 3, I get 120. And if I multiply 8 by 3, I get 24. So 120 plus 140 plus 24 is 144. And you see that Q2 is exactly equal to 3 times Q1. So that should remind you, oh, the way capacitors work is that specifically when they're in parallel, the lion's share of the charge goes to the larger capacitance, and the smaller amount of charge goes to the smaller capacitance. In resistances, what we know is when they're in parallel, the largest current goes to the smallest resistor, and the smallest current goes to the largest resistor. Okay, so it's sort of opposite of that, but that's why I did that. Now we can look on part B. And part B, you're asked to figure out what the new one is. So what's happened now is we have basically, let's say 48.0 microcoulombs on this charge, on this capacitor, excuse me, C1. And then that's connected over here to C2. And that one has, which is C2, that one has 144.0 microcoulombs there. But here's the thing, I've connected it where the positives line up with the negatives. So what I'm going to say here is this side, the C2, I'm going to treat as if it has the positives. And then this side, C1, I'm going to treat it as if it has the negatives. And what you see from that, remember, is that Q1, let's say Q2, I think I like that better so it comes out positive. Q2 minus Q1 is actually going to be equal to Q1 plus Q2. In other words, what's going to happen is because I've got 144 microcoulombs of positive charge, that's going to get hit 48 microcoulombs of negative charge. So those 48 negative microcoulombs of charge are going to be completely canceled out, and it's going to wipe out 48 of the 144. So that in fact leaves 96 microcoulombs of charge for them. So what that tells us is 96.00 microcoulombs is equal to Q1 plus Q2. Okay. Now, the other thing we know is that these two are in fact in parallel. Okay. Again, I explained to you how we know they're in parallel because it's obvious that they clearly have the same voltage. So because of that, we can say that V prime, which is the voltage they have, and that's the voltage symbol that I suggested you use in part B, V prime is going to be equal to Q over C. So that can be, for instance, in the case of the lowercase q's, that's going to be Q1 over C1. And we also have V prime is equal to Q2 over C2. Now, we don't necessarily, we do want to know V prime eventually, but right now what I'm going to do is I'm going to use the fact that V prime is equal to V prime so that I can say Q1 over C1 is equal to Q2 over C2. And that tells me that, for instance, Q1 is just equal to C1 over C2 times Q2. Well, C1 was the 2 microfarads, and C2 was the 6 microfarads. Notice the microfarads in the top and bottom are going to cancel out. So basically what I get is that Q1 is 1/3 Q2. So now I can plug that back into what I'm going to call equation 1. And this will be equation 2. So plug 2 into 1. When I do that, I get 96.00 microcoulombs is equal to 1/3 Q1 plus Q1, or excuse me, Q2 plus Q2. Okay, so 1/3 plus 1 is 1/3 plus 3/3, so that's 4/3. So that tells us that Q2 is equal to 3/4 of 96.00 microcoulombs. So I have Q2 is equal to 96 times 3 divided by 4 gives me 72 microcoulombs. So that's another answer. Now Q2 is the bigger one. So in principle, since Q2 is 3 times bigger than Q1, you'd expect that Q1 would be about 1/3 of 72. Well, 3 goes into 60 20 times, and then it goes into 12, which is what's left of 72, 4 times. So I'm going to assume it's about 24. But we can check that, and we'll see that Q1, oops, I'm going to use green. We're going to see Q1, which is equal to 1/3 Q2. So 72 divided by 3 is in fact 24. So this is 24.0 microcoulombs. So we now have Q1 and Q2. And finally, I can say that V prime. Does anybody think they know whether V prime is going to be smaller or bigger than 24 or equal to 24? Because remember, we used a 24-volt battery to charge it up. Anyone have an idea? The main thing is when I ask you these questions that you try to think if there's anything that tells you what the answer might be, then use that logic and make a guess. and then check yourself. If you find out you're wrong, try to figure out why. If you find out you're right, just pat yourself on the back. So I can just take, for instance, Q1 over C1. And of course, Q1 is 24 and C1 is 2. And in both cases, they're micro. So if I take 24, or excuse me, if I take Q1, which is 24, divided by 2, C1, which is 2, I get 12.0 volts. Any questions on that one? Now, I left a whole nother page to do that, but it turns out I didn't need that because I was able to fit it in here. So I'm just going to move on to the next page that has writing on it. Are we sure anybody has any, no one has any questions or anything? All right. So I'll deal with that page being missing later. What I wanted to do now is talk about the actual energy stored in a capacitor. And I remember when I went through this course, they did something like this derivation that you see to the right, but they used, for instance, VDQ. And that bothered me because I always use the formula Q times delta V, because that's the one, remember, that we use to define the electron volt, because you can take the charge of the electron, which is 1.602 times 10 to the negative 19th, and multiply it by the voltage, let's say 1 volt, and that gives you 1.602 times 10 to the negative 19th joules. And we define that to be 1 electron volt, which has the neat little symbol that looks like this. That looks just like charge times voltage. That's why I like it. It's Q delta V is equal to that. So that bothered me when they used VDQ instead of QDV. So what I decided to do when I was writing this up is I decided to do both ways and let you see what you get, so that you can see that it's not necessary that we do that one way. We can do it either way. And in fact, we can then use C equals Q over V, or Q equals CV, or V equals Q over C to get yet a third formula. So if we look right here, let me show you with my little pointer. If I look right here, QdV, I'm going with work equals the integral of F dot DL. What happens there is you can say F is equal to Q times E, and then E dot VL is basically dV. So you can say, let me put this in, this would be Q times E, and then Q times E dl. That is basically Q times dV. So that's how they get this middle integral right here. Okay. Now, if you remembered the formula that I just wrote for you, then you might want to use that formula. So I'm just going to do both. If I do Q dV, what I'm going to do is get Q in terms of V. Well, according to C equals Q over V, Q is equal to CV. So the integral of CV dV, since C is a constant, is 1/2 CV squared, which is the right answer. That's a formula for the energy stored in a capacitor when it's charged up to a voltage of V. Now, similarly, I can use VDQ, which we're just using based on that formula I just showed you instead of deriving it or whatever. But in using that, now I have to say, well, what is V? Well, V is Q over C. So I'm going to put 1 over C times Q, and then the integral of dq. So we get the integral of 1 over C Q dq. The integral of Q dq is 1/2 Q squared. So I get 1/2 Q squared over C. That's the formula. So you now see where this formula came from, and you see where this formula came from. Now, what we can do for the last one is I can go ahead and say V is equal to Q over C and put it in here. When I do that, then I'm going to get Q squared over C squared. So, well, that would actually just give you this formula again. Sorry about that. I was trying to remember what I did. Let's replace C with, I'll replace C with Q over V. So that's what I'm going to do. I'm going to replace this C with Q over V. Then you're going to have 1/2 Q over V times V squared. That's going to cancel out one of the V's, and you'll just have 1/2 QV, which is that formula. So if you have the charge and the voltage, you want to use this version. If you have the charge and the charge and the capacitance and the voltage, you want to use this one. If you have the charge and the capacitance, you want to use this one. If you have the charge and the voltage, you want to use this one. Does that make sense to everyone? Okay, so here's another example. And this is a typical use of a capacitor. If you've ever used a 35 millimeter camera with a flash on it, you'll sometimes hear that you take a shot and then you'll hear a zing, like this really high pitched noise. And what's going on is that is a noise they've manufactured or put in there, the manufacturers put in there, so you could hear the actual capacitor charging up. That tells you when that noise disappears that it's ready to make the next shot and it's fully loaded. So a flash bulb uses a capacitor to quickly deliver its current. How much energy is stored in the capacitor if it is a 500 microfarad capacitor with a voltage of 350 volts? B, if all the energy is used in 1 millisecond, what is the power delivered? So that's the problem we're going to solve here. I'm going to say solution. So we're looking for, in part A, we really want to find the energy stored. So we want a U. In this case, we have the capacitance and the voltage. So I'm going to use 1/2 CV squared. So that's 1/2 times 500.0 microfarads. Again, I put that on there so we can be assured that the 500 is all sig figs, and then times the 350.0 volts. That was actually supposed to be underlined as well. Let me do that real quick. Okay. So now I'm going to do 350 volts, and that's got to be squared. So I'm going to take 0.5 times 500. Notice I left the micro off. Times 350 squared. That gives me 3.063 times 10 to the 1, 2, 3, 4, 5, 6, 7 times 10 to the 7th micro joules. Now the micro is 10 to the -6, so that gives us that U is equal to 30.63 or excuse me, I can get rid of the micro now, 30.63 joules. Anybody have any questions on that? Just for the record, what I'm going to do is I am going to multiply this by 10 to the -6 because that's what the micro means. And that's going to leave 10 to the 1. And then 10 to the 1 times 3.063 is 30.63. That's where that came from. Any questions on that? All right, the next part is to calculate the power. So power is just dW over dt. I'll just remind you that we play a little fast and loose with power. So sometimes we'll say power is dW dt. Sometimes we'll say it's dE over dt. Sometimes we'll get crazy and just say it's du over dt. And that's really what the instantaneous power is. but the average power is just like W over T or E over T or U over T, that sort of thing. That's what we repeatedly say over and over again. So just keep track of that. It really is technically supposed to be dW dt, where W is the work done. But of course, work done could turn into potential energy. That's why you could also call it du over dt, or it could say turn into the total energy of the system. That's why we say du over dt. In this case, I'm just going to divide it, and I'm going to say that the average power is equal to 30.63 joules divided by 1.0 times 10 to the negative third seconds. And of course, division by 1 means nothing changes, but division by 10 to the negative third is the same thing as multiplication by 10 to the positive third. So we're going to say this is 30.63 kilowatts. Almost wrote kilojoules there. And that's the power. Anybody have any questions on that one? I hate this because I really want you guys to be interactive, and I feel like I might be just steamrolling you. I don't want to steamroll y'all by just going through all the problems really quickly. Does anybody have any questions on anything I've done so far? Okay. I'm putting this here. I'm going to paste the page. And then I'm going to remove the page. Nope, I'm not going to do anything because it won't let me do what I wanted to do. Clear page. Nope. Move page to trash. That works. Okay, so now I've got it fixed where they're immediately after each other. So still not getting any questions. So I'm assuming I'm not steamrolling you guys. That's really my biggest fear. So we'll move on. Oh, now we got 2 pages of the same thing. That's super helpful. I'll tell you what I'm going to do. I'm going to go back here and we'll copy this page. And I'm going to go back here. And I'm going to paste the page. And now I'm going to now I'm going to delete this page. And I got that and I got that. Okay. Poop. I did not mean to put that there. Oh, well, let's move on. I'll worry about that later. So now I have a conceptual example. Example 3, a parallel plate capacitor is charged to a charge Q, and then the battery is disconnected. The plates originally separated by a distance D are then pulled apart to a distance 3D. How has the energy stored in the capacitor changed? So first off, I want to talk to you about what happens when you disconnect a battery versus keeping the battery connected. If you keep a battery connected on a capacitor, what you're doing is assuming the battery's properly charged and working correctly, then it locks that voltage to the voltage of the battery. So for instance, a 12-volt battery would maintain a constant 12 volts across the capacitor if you left the battery connected. However, if you disconnect the battery, then the actual capacitor is now isolated. It's all by itself. No charge can go anywhere. So in this case, the voltage is free to move up and down, but the charge has to stay constant. So that's the key thing to understand here. So write that down in notes, in your notes if you have to, or do something with it. Just so you can keep track of it, because that's a big concept that comes up in problems. And if you don't realize, hey, when I leave the battery connected, the voltage is locked down and the charge can change because charge can flow back and forth between the battery and the capacitor. But when I disconnect a battery, then the voltage can change, but the charge has to stay fixed. Okay. So our solution really is to look at U, because they want to know how has the energy changed. Well, U is equal to, in this case, we've got Q and we've got a distance. So in principle, we should be able to make something out of the C that's going to matter. And we're going to have to use something with Q. Because the battery is disconnected, Q can't change. So using the Q version of the formula is a good thing. If we look back at what the formula was that involved Q and C, we can see that this is a good one to use, 1/2 Q squared over C. So I'm going to say U is equal to 1/2 Q squared over C, and C is equal to epsilon 0 A over D initially. Afterwards, the final capacitance is epsilon 0 A over 3D, like that. Okay, so U initial is equal to 1/2 Q squared times 1 over epsilon 0 A over D, which equals, let's say, Q squared times D over 2 epsilon 0 A. U final, on the other hand, is equal to 1/2 Q squared. 1 over C is now going to be 1 over epsilon 0 A over 3D, which becomes 3 Q squared D over 2 epsilon 0 A, like that. So what we see is the change in energy, delta U, which is U final minus U initial, is in fact, since I have a common factor of Q squared D over 2 epsilon naught A, I'm going to pull that out in front, Q squared D over 2 epsilon naught A. Now the difference is the final one has a 3 on top, and the initial one has a 1 on top. So 3 minus 1 becomes 2, and that cancels out. So I get Q squared D over epsilon naught A. So what we see is that the energy actually increased. The change in potential energy was a positive quantity, so the potential energy actually went up. Now, physically, let's think about what that means. You have a parallel plate capacitor, which you can see is two plates like this. One's positive and one's negative. Because they're oppositely charged, they have an attraction for one another. The negative plate is attracted to the positive plate, right? So you pulling it apart is going to mean you're going to have to put some work into it because they don't naturally repel one another. They naturally attract one another. So if you actually put work into the system by applying a force to each side to pull them apart, you're actually putting work into the system, and that gives you what you expect, which is the increase in potential energy. And we just calculated that, so we know that it's right. Anybody have any questions on that? Now, really, that the conceptual aspect of it really is handled by that series of sentences I said after I solved it. And then mathematically, I showed what it would actually be. So that's going a little bit beyond it. But sometimes you need the math to help you with the concepts. Sometimes you need the concepts to help you with the math. In this case, I'm banking on you're less familiar with the concepts of capacitance and how capacitances behave than you are with the math. So I tried to show you it in math and then explained it after the fact in concepts. Does everybody understand that? Does anybody have any questions on how that came to be? Okay, no one's typing anything, so I assume that's good. All right, let's go on to our next one. So here's example 4. It says a parallel plate capacitor has an area A, a separation D, and is charged to a voltage V. With the battery still connected, so this time the battery is going to stay connected instead of being disconnected. With the battery still connected, the plates are pulled to a distance 3D. Sounds a lot like the last problem, except now we're doing it a little differently. A, what are the initial and final energies stored? B, assuming the separation is done slowly, what is the work done in separating them? and then C, how much energy is exchanged with the battery. So we're going to work that. I used purple last time. I'm going to use purple this time for my solution. Now this time we have A and D, which are typically parts of C, the capacitance, and we have the V. And since the battery is going to stay connected, V is going to be locked down. So we want to use the 1/2 CV squared formula for the energy. So the potential energy stored is 1/2 CV squared, and we know C is equal to epsilon 0 A over D. So that's important. What we're going to have initially is CI is equal to epsilon 0 A over D. And what we're going to have after the fact is C final is equal to epsilon 0 A over 3D. Okay. But since the battery stayed connected, the Q can change all at once because charge can flow back and forth between the capacitor and the battery, but the voltage is going to be locked down. So for part A, U initial is equal to 1/2 epsilon 0 A over D times V squared. So I'm going to say it's epsilon 0 A V squared over 2D. That's the initial energy. The final energy, UF, is going to be 1/2 epsilon 0 A over 3D times V squared. So this time it's going to be epsilon 0 A V squared over 6D. Okay. So those are our two energies before and after. Now you can see that the other one's like 1/2 epsilon 0 AV squared over D, and the second one is 1/6 epsilon 0 AV squared over D. So actually delta U is negative. Delta U, which is U final minus U initial, would be 1/6 minus 1/2, and all that times epsilon 0 A V squared over D. Of course, 1/6 is the same. Well, 1/6 is fine. If I want to get a common denominator, then I want to multiply 1/2 by 3 over 3. So it's 1/6 minus 3/6, which gives me negative 2/6. So the answer is negative 2/6, which actually is equal to negative 1/3. So negative epsilon 0 A V squared over 3D. That's the change in potential energy. But I wasn't really asked that. I just wanted to show you that it does, in fact, come out negative. Anybody have any questions on that? Now, B is really the complicated part. So let's go over that. Again, anybody have any questions on part A so far? All right, so work is equal to the integral of F dot DL. In this case, you can see the force is going to be exactly parallel to the electric field that's created by the parallel plates. So we don't have to worry anything about the dot product. So I'm just going to make that clear right now. Now I'm going to replace F with Q times E. And then I'm going to say times DL like that. Okay. Now, what I have to do is I have to figure out what the electric field is. Now, the deal is we're going to have a capacitor that's charged up to Q. And one plate, say, will have a charge of positive Q, and the other plate would have a charge of negative Q. And one of those plates can be seen as creating an electric field, and the other plate is seen as moving through it. That's a little different than what we thought about before, because before what we did is we calculated the electric field between the plates by realizing that the positive plate caused an electric field and the negative plate caused an electric field that pointed the same way. So we ended up getting sigma over 2 epsilon naught plus sigma over 2 epsilon naught became sigma over epsilon naught. Okay. In this case, we can't compute or can't use the whole electric field because part of that electric field has been created by the one that's moving, that's doing the moving. So what we're going to do is we're going to go ahead and replace the actual electric field. We're going to say that V is equal to E times D. So I think that works pretty well. V is equal to E times D. That's what we found for the parallel plate capacitor when we calculated V equals the negative integral of E dot dl. So in this case, we can say E is actually V over the separation. What I'm going to do is call the separation, let's say L. So I'm going to go ahead and write this as Q times, now in this case, I'm going to say V over 2 is the electric field. Any questions on that part? Okay, so now I'm going to say, since Q is equal to, well, I'll write it over here on the side. We know that C is equal to Q over V, and that means Q is equal to CV. So what I'm going to do is replace the Q with C times V. Well, C is epsilon 0, I'll put the integral, epsilon 0 A over L is the capacitance at any particular position in time or whatever. And then V is just going to be V. And then I have V over 2 like that. And then I have, let's see. Oh, I forgot my V over 2L. Sorry about that. Remember, the voltage is, or excuse me, the electric field is the voltage divided by L. But since we're only computing the electric field due to one of the plates, I had to multiply that by 1/2. So that should be V over 2L, not V over L, or not V over 2. I don't know why I wrote it that way. But now you can see what happens. I'm going to get basically the epsilon 0, the A, and the V squared all comes out in front, and the 2 is on the bottom and can come out in front. And now I have the integral of, oh, and I forgot the dl here, the integral of dl over L squared. Now the integral of L to the negative 2 is L to the negative 1 divided by negative 1. So I'm going to say this is negative epsilon 0 A V squared over 2 times. Now I've already taken care of the negative sign. Now I just get 1 over L, and that's going to be evaluated. First, we're basically going from D to 3D. So this is going to be negative epsilon 0 A V squared over 2 times 1 over 3D minus 1 over D. Now notice 1 over 3D is inherently smaller than 1 over D. So when I do that subtraction, I'm going to get a negative, which is going to cancel out that negative up front. So I'm just going to go ahead and erase that negative out in front and change the order. So this is going to be epsilon 0 A V squared over 2 times, now to get a common denominator, I'm going to multiply the top and bottom of 1 over D by 3. So this is going to be 3 over 3D minus 1 over 3D, like that. And that's going to give me epsilon 0 A V squared over 2 times. Now 3 minus 1 is just 2, so this is going to give me 2 over 3D. So finally, I can say the work done is actually equal to 2 epsilon 0 a v squared over 3d. Oh, that 2 canceled out. Sorry about that. Let's just erase the whole thing and start over. Okay, so the 2 in the top and bottom canceled out. I'll do that by showing this and this. Okay, and now I can go ahead and write that I have epsilon 0 a v squared over 3d is the work done. Anybody have any questions on that one? Okay, so Ethan asked me, where did I get v over 2 from? Did you hear my explanation and now understand it, or do you still need me to answer that?
Yes, I did. I asked that before you clarified.
Well,
Thanks.
yeah, don't forget it was supposed to have the L under there, so that was my boneheaded mistake. All right, so now we can go back and find part C, which is how much energy is exchanged with the battery. So part C, what we're seeing here is that I'm doing a certain amount of work, and that work is going into changing the potential energy of the capacitor plus changing the potential energy of the battery. What we want to know is delta U of the battery, which is clearly equal to work minus delta U of the capacitor. And now you see why I took time to actually calculate the delta U of the capacitor. So what I'm going to say is delta U battery is equal to the work, which we found was epsilon 0 a v squared over 3d minus, now that delta U was negative, so I had negative epsilon 0 a v squared over, and looks like I did to get 6d. I think that's correct. Let me double check that. I don't remember having a 6 before. Let's see if I made some kind of careless mistake. 1/6 minus 3/6 is negative 2/6, which is 1/3. Where did I get that? Oh, I see. I copied the wrong thing. What I was supposed to copy was that, not that. So yeah, it's not supposed to be a 6 down there. It's supposed to be a 3. It's really hard looking at all this stuff and seeing what's going on there. So what we can see now is I've got epsilon 0 a v squared over d times 1/3, and then minus a minus means plus, again times 1/3, the exact same thing times 1/3. So I get 1/3 plus 1/3 is 2/3. So this becomes 2 epsilon 0 a v squared over 3d, and that's the changing of the potential energy of the battery, or the stored energy of the battery, which is a nicer way of thinking about it. But what that tells you is by pulling those plates apart, I've actually change the energy stored in the capacitor in the battery by a positive amount. That means I've basically charged the battery. So if you connect a battery to a capacitor, a parallel plate capacitor, and you pull the plates apart, that's going to take some work because the plates are attracted to each other. And that work is actually going to go into to create energy in the battery and in some sense charge it. Obviously, that also means if you do too much, you could actually overheat the battery and run into other problems. Anybody have any questions on that? All right. So now that we have that, we're going to do something else that's sort of a look to the future, but it's also something that's fundamental. Like in principle, we know that just like an ocean wave is a ripple like this, and it's coming into shore. And when it gets to you, let's say you're out swimming past the breakers, past the second sandbar, basically, and you're swimming, and this wave comes to you. When the wave comes to you, it's first off going to pull you back like out to sea a little bit, because the wave isn't just a transverse wave. It's a little bit transverse, but it's also a little bit longitudinal. So you end up doing this sort of motion. So first off, it's going to bring you back. And in fact, you're going to get in the trough. So it's going to bring you back and down. And then the crest is going to come by and bring you forward and up. And then you end up right back where you started from. In order for that to happen, that wave must be carrying energy, because it just gave you some potential energy. Although it took it right back, it took you from sea level to sea level plus the height of the wave. And that took energy. That took a change in potential energy. So clearly the wave's carrying energy. Well, guess what? If you talk about electromagnetic radiation, what we call EMR, electromagnetic radiation is basically all the parts of electromagnetic radiation include gamma rays, X-rays, ultraviolet, visible, infrared, microwaves, and radio waves. Okay, all of those are all types of electromagnetic radiation, and we'll ultimately learn what that is. But right now, what that means is an electric field oscillating in one plane, and then perpendicular to that is an electric field, or excuse me, is a magnetic field oscillating in another plane, and then in a third direction is the propagation. So in fact, if you did your hand of your right hand, if you did it like this, where you have your index finger pointing straight out, your middle finger pointing perpendicularly to your palm, and your thumb pointing perpendicularly to both of them, then what that means is if you put this in the direction of the positive electromagnetic radiation, so the electric field is going to oscillate up and down. So we take, at the time when it's up, we put our finger up, and then we rotate our hand so that my middle finger now is pointing in the direction of a positive magnetic field, and then my thumb points in the direction of the velocity of the wave. That turns out to be what actual electromagnetic radiation is in terms of waves. Well, just like a wave in the ocean carries energy, we would like to know how much energy does an electromagnetic wave carry? So what we can do is we can take a particular electric field and just find out, hey, how much energy is stored in an electric field? Well, one example we know of is the electric field created by a parallel plate capacitor. So I'm going to calculate that and see if I can reduce it down to something that has nothing to do with the capacitance, but specifically with the electric field. And lo and behold, when we do that, we'll actually get an answer that happens to be the right answer. So what we're going to do is calculate the the energy stored in a parallel plate capacitor. So the energy stored in a parallel plate capacitor, one of the versions we learned was 1/2 CV squared. So if I take a parallel plate capacitor with air or with a vacuum in between the plates, then it's 1/2 times the capacitance. And of course, the capacitance is epsilon 0 A over D. And then we also learned that the voltage is the electric field times D. So the V squared becomes ED squared. When I multiply all that through, I get 1/2 epsilon 0 A over D times E squared D squared. You can see that the D here cancels out with the D here, and I get 1/2 epsilon 0 E squared times AD. But remember, A is the cross-sectional, or the area, the surface area of the plate of the parallel plate capacitor, and D is the separation between them. So A times D is an actual volume, and that volume is the volume between the plates of the parallel plate capacitor. Now, we know the electric field goes a little bit outside of the capacitor, but the vast majority of the electric field is entirely in that little volume AD. So we can think about the energy density, which would be the total energy divided by the volume. That symbol is lowercase u. The uppercase u we already calculated is there, and then we're going to divide it by the volume, which is AD. When we do that, we get 1/2 epsilon 0 E squared. It turns out that that's the right answer. In other words, if we do it properly with all the laws of electricity and magnetism and Newton and all that good stuff, and we work out exactly how much energy is stored in an electric field, what we find is the energy is 1/2 times epsilon 0 times E squared. So the energy is directly proportional to the square of the amplitude of the electric field. Now, I will say that we can get a little fancier. For instance, if we talk about the energy in an electric field in a dielectric, then U in a dielectric is equal to 1/2 epsilon E squared, where epsilon is equal to the dielectric constant times epsilon 0. So this is in fact another formula that's extremely important. So we have that one, but if we want to find the electric field, or excuse me, the energy density of an electric field in a dielectric, which again is a fancy word for a insulator, then this is your guy. Any questions on that? So the energy density is 1/2 epsilon 0 E squared, or 1/2 epsilon E squared. And that has units of joules per cubic meter. And then I work out exactly why we know it's joules per cubic meter. Mainly the 1/2 has no units. So we really only care about the epsilon 0 and the E. And E is in volts per meter. Epsilon 0 is in coulomb squared per Newton meter squared. So that's where all that came from. You can see it worked out there. That's something, by the way, that all of you guys should be able to do. So make sure y'all can work with your units that way. Anyone have any questions on that finding? Okay. And I've got another blank page and another blank page. All right. So what we're going to do now is we're going to talk about capacitance in a more robust way, where we're going to actually work some problems. Your book goes into section 24.4-1, which is the health effects. Specifically, it talks a little bit about a defibrillator. That's the main thing it's talking about there. That's very important stuff. Not only that, it's probably important as a scientist for you to understand that there's no magic that we know of in life. There's not any magic that makes your heart beat. It's just electricity. There's no magic that makes your brain work. That's just electricity. There's no magic that makes you feel someone poking you in the finger. That's just electricity. So that's part of what you should understand as a scientist. And this talks a little bit about it, about how you can use the electricity to reset your heart in some way with the defibrillator. But the big thing to remember is really what causes the contraction of the heart is why we can do an EKG, or what's also called an ECG. So read over that stuff. You should read as much of this book as you can, and especially the sections that have little or no math. That's where all the concepts and where a lot of the big physics principles come in. So I definitely want you to read that as much as you can. I'm going to go on to dielectrics. Again, what we've already told you is that if you have a capacitance C, which equals epsilon 0 A over D, say, if you take that, which is really just a parallel plate capacitor like this with air or a vacuum, if you have that, then that's what the capacitance is. However, if you have a capacitor that has a plate and another plate, and then you put a dielectric in between it, and it fills the whole space. I'm trying to show you that here. Let me do this. Let me draw the dielectric as if it's red. And then I'll draw the parallel plate as if it's blue and blue like that. Then it turns out when we have that, this quantity would be called C0. The new quantity would be K epsilon 0 A over D, which we can also call just plain epsilon A over D. Okay. And the dielectric constant is given in table 24-1. So for instance, it says for a vacuum, the dielectric constant is 1.0000. That's all it says. But in reality, as far as we can tell, the vacuum should have a dielectric constant of 1 exactly. Air, which is very close to a vacuum, but not that close, has a dielectric constant of 1.0006. So K air is equal to 1.0006. And that's a dimensionless quantity, by the way. Okay. And it has a dielectric strength of 3 times 10 to the 6 volts per meter. What that means is how big of an electric field do you need to actually cause that dielectric to become a conductor? If you put an electric field of 3 million volts per meter between the plates and the plate is only separated by air, the capacitor will fail. Lightning will strike. Basically, negative charges will leave the negative plate and jump to the positive plate going through the air. Some other dielectrics, for instance, are paraffin. That has a dielectric constant of 2.2, so you can more than double the capacitance. And it has a dielectric strength of 10 million volts per meter. So that actually gives you a bit more protection from ruining your capacitor. Polystyrene, which is a fancy word for styrofoam, has a dielectric constant of 2.6, and it has a dielectric strength of 24 million volts per meter. Vinyl, which is what a lot of people's leather is made out of, that has a dielectric constant, depending on how you make it, of somewhere between 2 and 4, but it generally takes 50 million volts per meter to break it. Paper 3.7, 15 million. Quartz 8, 4.3, and 8 million. Oil, just regular motor oil is what I'm suspecting here, is 4, and then the dielectric strength is 14 million. I will tell you that we used to use as a dielectric PCB oil, and PCBs are actually very, very carcinogenic, and I've had a buttload of it spilled on me by accident, and I'm already a hypochondriac, so that wasn't a good thing. So literally every day I freak out about it. But if you ever find the old electronic equipment and you find something liquid in it, you want to stay away from that, okay? Because that was often used as a dielectric, and it turns out it was cancerous. So we're slowly getting rid of that. But some of the transformers you might see, for instance, up on telephone poles, those big bucket looking things that are shaped like a really big bucket and have like these tall tower things sticking off of them that look sort of like Christmas trees. Those are actual transformers, and some of those might still have some PCBs in them. Long as they're not messing up, long as they're not leaking, long as you haven't just thrown it away, it doesn't really pose any harm to you. But when you do throw it away, it can pose harm. They also do things like porcelain, rubber, mica. Mica, by the way, has a dielectric constant of 7, and 120 million volts per meter is a dielectric constant. So mica is particularly good. Water, on the other hand, has a dielectric constant of 80, and it takes 70 million volts per meter. Strontium titanate has a dielectric constant of 300, but only has a dielectric strength of 8 million volts per meter. Okay, now that we have that, we can do something kind of neat. So let's look at this conceptual example. So the conceptual example is an air-filled capacitor has a capacitance C0. So listen to me closely, or if you happen to have a copy of your textbook, that would be a worthwhile thing for you to look at. That's what I'm looking at right now. In fact, let me go ahead and stop sharing my screen and let me share the screen with something else. So now I'm going to share screen with my actual textbook. So this is the conceptual example we're talking about, and I care mainly about the question because we're going to go over the answer ourselves. It says an air-filled capacitor of capacitance C0 consisting of two parallel plates separated by a distance d is connected to a battery of constant voltage V equals V0 and acquires the charge Q0 while it is still connected to the battery. Okay. A slab of dielectric, while it's still connected to the battery, a slab of dielectric with K equals 3 is inserted to fill the space between the plates of the capacitor. You got to do that very carefully so that you don't steal any charges or change the separation and stuff like that. But we're slowly going to slide a dielectric of K equal 3 in between the plates. Will the Q increase, decrease, or stay the same? So what we want to know, since it is an air-filled capacitor, C0, consisting of two parallel plates separated by a distance d and connected to a battery. So notice it's still connected to a battery. What we learned is when it's connected to a battery, what is locked into place? Is it the voltage? Is it the charge? Is it the electric field? Is it the capacitance? What is it?
The voltage.
Yes, when it's connected to a battery, the voltage is locked in. So you can think about the energy, for instance, as U equals 1/2 CV squared. In this case, the C is definitely going to change, but the V is going to stay the same. So if we replace C with 3 times C, you can see the energy would actually increase by a factor of 3. What they're asking here, though, is what will Q do? Well, here's the trick to making sense of that. The actual capacitance C, remember, is Q divided by V. There's no way of getting around that. That's the definition of capacitance. It's the charge divided by the voltage. Okay. Well, we know for a fact by slipping the dielectric in between the plates, the capacitance is going to increase by a factor of 3. So C equals Q over V goes to 3C0 equals some new Q over V because V can't change. So in order to accommodate that factor of 3, what has to happen to the charge?
Increase 3 times.
Exactly. And that's the answer. So it says, since the capacitor remains connected to the battery, the voltage stays constant and equal to the battery voltage V0. The capacitance C increases from C0 to K times C0 when the dielectric material is inserted because K has increased. From the relation Q equals CV, if V stays the same, but C increases, Q must increase as well. So that's the example. Anybody have any questions on that? Now let's look at this next one. Suppose an air-filled capacitor of capacitance C0 is charged to Q0 and then disconnected from a battery of voltage V0. Next, the same dielectric is inserted between the plates. Will Q, C, or V change? Anybody want to take a poke at that? And don't feel bad for being wrong. It's certainly fine. That's why we're learning.
Would V change?
V can definitely change and will. That's very good. Okay. What about Q? Remember the other part that I said about when you disconnect a battery, you've now isolated the capacitor, so charge has nowhere to go. So the charge is going to have to stay the same. Will C change?
Yes.
Yes. In this case, C is going to change again. And in fact, C is going to increase by a factor of 3. But C is equal to Q over V, and we said Q can't change. And you did say V would change. So what's V going to do? Is it going to increase or decrease or stay the same? Or, well, we already decided that it's going to change, but is it going to increase or decrease?
Increased by 1/3.
Exactly. It's going to decrease by 1/3. That's really the key point here is C is equal to Q over V. If Q stays the same and C goes up, that has to be done by V going down by a factor of 3. If, on the other hand, if we actually had it connected to a battery, then the V has to stay the same and the Q has to change. But in that case, the Q has to increase, whereas the V had to decrease. So yes, the response your author says is the charge Q0 remains the same. The capacitor is isolated, so there's nowhere for the charge to go. The capacitor, though, increases as a result of inserting the dielectric to C equals K times C0. The voltage across the capacitor also changes. The voltage decreases by a factor Q equals Q0 equals CV. So V is equal to Q0 over C, or Q0 over K C0, which equals V0 over K, where V0 is Q0 over C0. So yeah, you see that it decreases by a factor of K. That answer right there, V is equal to V0 over K, is really important. Your textbook used to have a series of sentences. I haven't found them yet, so I don't know if I just hadn't read it enough recently or what, but it had these sentences that were really valuable, and they were experimental results. The experimental results basically said, hey, if you take a battery, take a capacitor and connect it to a battery, and you leave the battery connected. If you then try to insert a dielectric carefully between it, what we find is if you leave the battery connected, then the voltage can't change. That's going to cause the capacitance, of course, since you're putting the dielectric in, that's going to cause the capacitance to go up. And the only way the capacitance can go up, since the voltage can't change, is the charge is going to increase. Now, if you do the same experiment, but this time you remove the battery and isolate the capacitor and then slide the dielectric in, well, now the Q can't change, but the C changes. Okay. So the C is again going to increase by a factor of K. And the only way we can accommodate that, since Q doesn't change, is V's got to go down by a factor of K. So the voltage is now going to be V0 over K. Okay, so these were some experimental results that your book, your author took in the 4th edition time to write down. I haven't found them in the 5th. It might just be that when I looked yesterday or the day before yesterday when I looked, I just didn't see them, but they might still be in there. But the important thing is that you understand that's what happens when you try to shimmy a little dielectric into between the plates. In the case of leaving the battery connected and in the case of not leaving the battery connected. But that should be somewhat common sense. But now we actually have, by him telling you these are experimental results, we know that it is exactly what we expect. There's only 2 ways to change capacitance. Well, sort of 3 ways. You can change the charge, or you can change the voltage, or you can change them both. But if you change them both by the same amount, that's not going to change. So for instance, if you double the charge and double the voltage, the capacitance is still the same. But if you double the charge and triple the voltage, then the capacitance is going to go down by a factor of 2/3. All right, here's where it said what I just finished telling you about E in a dielectric. Notice the energy density is 1/2 epsilon E squared. All right. Now, the other thing to know is right here, it says an electric field is also altered when a dielectric is inserted. When no dielectric is present, the electric field between the plates of the parallel plate capacitor, for example, is just V0 over D, where V0 is the potential difference between the plates and D is the separation. If the capacitor is isolated so that the charge remains fixed on the plates, then a dielectric is inserted. filling the space between the plates, the potential difference drops to V0 over K. So the electric field inside the dielectric also drops to E0 over K. That is important. And it says something very important here. The electric field in a dielectric is reduced by a factor equal to the dielectric constant, but the field in a dielectric or insulator is not reduced all the way to zero as in a conductor. Equation 2410, here's the important point. Equation 2410 is valid inside the dielectric, even if the dielectric's thickness is smaller than the gap between the capacitor plates. Okay, so in other words, if you put a dielectric between the plates and it doesn't fill the whole space, the electric field inside the dielectric is going to become the original electric field divided by the dielectric. So that's another key result that we're going to make use of. Now's a good time for us to go ahead and take a break. It's 6:51. So let's say you 6:52 now. Let's go ahead and say you come back at 7. I will sit here the whole time, but if anybody has any questions, you can ask me, but you're free to go. And I'll give you like a warning at 2 minutes till and 1 minute till. So go ahead and take a break, everybody. Feel free to ask me questions if you have them. I might actually fix up my sheet here, getting rid of those empty pages, and go ahead and copy the next thing in. Let's see. That looks good. Hey, buddies. What you boys doing? I see you. Yeah, good boys. All right, it's enough, buddies. All right, got about 2 minutes left, everybody. I do not. I think you do. That's enough. All right, it's time to start. I was in the process of writing out an example, so let me go ahead and finish it. It says, I'm going to go ahead and share my screen. And I'm in the process of writing out this next example. Maybe. Come on now. Okay, there it is. So a parallel plate capacitor is filled with a dielectric with K equal 4.00 is connected to a 120 volt battery. After the cap is fully charged, the battery is disconnected. The plates have an area of 4 square meters and are 2 millimeters apart. Find C0, Q0, E0, and U0. B, okay, so this is the second part. And for B, they want to find the dielectric is then carefully removed. Ooh. Okay, so actually I should remove all those zero subscripts because I usually use those for a capacitor without a dielectric. So I'll just do it like that. I wasn't sure how I wanted to work it. So this is E, this is Q, and this is just plain C. So we want to know all that for the capacitor. And then B, the dielectric is then carefully removed without changing the plate separation, nor does any charge leave the capacitor. Find the new values of capacitance, electric field strength, voltage between the plates, and energy stored in the capacitor. So the dielectric is removed. Carefully. Find, in this case, they're saying they want to find the new values of capacitance. So C, the new value of electric field strength. So E, the voltage. So V, and the energy stored in the capacitor. So U. So that's the problem we're attempting to solve. Anybody have any questions about that before we get rolling? Okay, so what we have here is C is equal to K epsilon 0 A over D, and C0 is equal to epsilon 0 A over D. We've got A is equal to 4.00 square meters. That's good. That means it's in our base unit, so we don't have to change it. So just remember, whenever we give you an equation, unless we explicitly tell you otherwise, the equation is supposed to have the proper units. If it's mass, it's got to be kilograms. That's the only one that has a prefix, by the way. If it's velocity, it's got to be meters per second. If it's area, it's got to be meters squared. If it's volume, it's got to be meters cubed. If it's distance, it's got to be meters, so on and so forth. We also have D is equal to 2.00 millimeters. And we also have K is equal to 4.00. That has no units, by the way. And we also have V0 is equal to 120 volts. Okay. So for part A, what we want to know is C. C is equal to 4.00 times 4.00 meters squared over, oops, I left off of epsilon 0. Because the formula is written a very specific way, I don't want to just throw that in at the end, so I'm going to correct it. So it's 4.0 times 8.85 times 10 to the negative 12th coulombs squared per Newton meter squared. That's where I had the units earlier, where I showed you that the units of energy density is actually joules per meters cubed. So this is the K epsilon 0. Now I've got the A, which is 4.00 meters squared. And then I have the D, which is 2.00 times 10 to the negative third meters. So I'm going to do 4 times 8.85 e to the negative 12th times 4 and then I'm going to divide that by 2e to the negative 3. That gives me 7.08 times 10 to the negative 8 farads. We can actually make that a little better as well. We could say C is equal to, if I want to make it 10 to the negative 9th, that would be nano. So I could divide this by, I could divide the 10 to the negative 8 by 10 and multiply the 7.08 by 10. That would give me 70.80 nanofarads. So that also is a correct answer. Now we also want to know Q. Well, Q, oops. From C equals Q over V, we get Q is equal to CV. So Q is equal to 7.080 times 10 to the negative 8 farads times 120.0 volts. I just did that to make sure everybody agreed with me that all three of the digits of the 120 are significant. So I'm going to multiply the 7.08 times 10 to the negative 8 times 120, and that gives me 8.496. One extra sig fig times 10 to the negative 6 coulombs, which is 8.496 microcoulombs is equal to Q. Now I'm going to box that off so we can remember it as well. Now I need to find the E, and there's a couple ways we could find the E. I'm going to take the harder one first. So the harder one is that the electric field is actually equal to sigma over epsilon naught, and sigma is actually the charge, sigma is actually the charge divided by the area. So what I can do is I can say the charge, which is 8.496 times 10 to the negative 6 coulombs, divided by the area, which is 4.00 meters squared, times 8.85 times 10 to the negative 12th coulomb squared per Newton meter squared. Okay. So now if I do that, I'm going to take 8.496 times 10 to the negative 6, and I'm going to divide it by parentheses 4 times 8.85 e to the negative 12th, close parentheses, and that gives me 2.40 times 10 to the 1, 2, 3, 4, 5 times 10 to the 5th volts per meter. So you can actually say that's 240 kilovolts per meter is another example of that, or another way of saying that. But you can see it's a pretty good size voltage, or excuse me, a pretty good size electric field. Now you could also have said E is equal to V over D. That would work as well because we already know what the voltage is. That's 120 volts divided by 2.00 times 10 to the negative 3rd meters, which I think you can see is going to be 2 divided by 120 divided by 2 is going to give you 60. Ooh, wait a second, wait a second. V is equal to ED, that works. 120, and D is 2 times 120,000 divided by 2 is 60,000. I don't know why I'm getting that different. Anybody get the same answer I did when I calculated the electric field strength? The Q we found, then I divide it by A, which is 4. Then I divide that by 8.85 to the negative 6. I'm going to try this answer again. 8.496 e to the negative 6 divided by parentheses 4 times 8.85 e to the negative 12th in parentheses. Yeah, I still get 240,000. I did use 120 volts, so it all works. I'm not sure why the V over D is not working, but I will leave that be. I'll think about it to some extent, but right now I'm just going to leave that be. That should be correct. Remember, the electric field for a parallel plate capacitor, one plate is sigma over 2 epsilon naught. The other plate is sigma over 2 epsilon naught. They both point in the same direction, so you get sigma over epsilon naught. And sigma is charge per unit area. So the total charge we found was 8.496 times 10 to the negative 6. And then all we had to do was divide that by A to get the sigma, and then divide that by epsilon 0 to get the electric field. I'm going to go with it right now and leave that be. I'll try to see if I can figure out something about why I screwed up in the voltage. V is actually equal to E times D, so E should be V over D. I don't know why it didn't come up that way. So it should have been 120, yeah. Okay, so anyways, we've got E. Now I'm looking for U. And U, in this case, we can use various formulas, but 1/2 CV squared works. So I'm going to have 1/2 times the capacitance, which is 7.080 times 10 to the negative 8 farads. That's going to be multiplied by 120 volts squared. So 0.5 times 7.08 e to the negative 8 times 120 squared. That gives me 5.098 times 10 to the negative 4th joules. And that's the energy stored. So that's what they wanted for part A. Now for part B, notice they said the 120 volt battery was connected. It was fully charged, and then after the capacitors, which we call caps, were fully charged, we disconnected the battery. So that means the voltage is free to move, but the charge is going to have to stay the same. Now we're going to do part B, and we're going to not only allow the charge to change, allow the charge to stay the same while the voltage changes. We're also going to extract the dielectric, so we're going to get a different value for everything. So now I can calculate C0, E0, V0, and U0, because these are specifically the cases in which we don't have a dielectric. So first off, C is just equal to epsilon 0 A over D. So that's going to be 8.85 times 10 to the negative 12th Coulomb squared per Newton meter squared. A is going to be 4.00 meters squared, and D is going to be 2.00 times 10 to the negative 3rd meters. So 8.85 e to the negative 12 times 4 divided by 2 e to the negative 3 gives me 1.77 times 10 to the negative 8th farads. That's C, what I call C0. And that should be C divided by 4, basically. So if I did 77.08 e to the negative 8, if I divide that by 4, I get 1.77 times 10 to the negative 8. So that's exactly what we expect, just double checking it. Now we're going to find E0. In this case, what we see is E0 is going to actually increase, because what we know happens when you actually disconnect a battery is the voltage can change and the electric field can change, and they both go down by a factor of K when you put the dielectric in. So that means they're both going to go up by a factor of K when you pull the dielectric out. So I can now say that the electric field E0 is going to be basically K times E. You could also use, sigma over epsilon naught, that kind of thing. But basically what I'm going to do is I'm going to say it's 4.00 times the electric field, times the original electric field strength, which was 2.400 times 10 to the 5th volts per meter. So 2.4 e to the 5th times 4 gives me 9.600 times 10 to the 1, 2, 3, 4, 5 times 10 to the 5th volts per meter is equal to E0. Any questions on that? Now, of course, you can do it other ways too. You could also say E is equal to V over D, but we had some problem with that a second ago. Let's check it now. E0 is equal to V over D. Since the battery's been disconnected, we could, in fact, have a very different voltage. So, in fact, what we know is the voltage is going to go up by a factor of 4. So in this case, I'm going to say 120 volts times 4.00, because just like the electric field went up by a factor of K, the voltage should go up by a factor of K as well. So this is going to be divided by 2.0 times 10 to the negative 3rd meters. And hopefully this one will come out the same, unlike the last experiment I tried. Actually, that looks really horrible. So times 10 to the negative 3 meters. So this is going to be 120 times 4. That's 480. Now I'm going to divide that by 2 e to the negative 3. And that's going to give me 24,000. Whoa, whoa, whoa. That's weird. Ten to the 1, 2, 3, 4, 5 times 10 to the 5th volts per meter. So again, you see something crazy that happened here. Again, I'm not sure why this isn't working. I worked this earlier. In fact, I've worked it twice earlier, and I didn't have these problems. So I don't know what's going on here. I'm sure I'm missing something really minor. So I'm just going to erase it and leave that be, and just say that there's good reason to suspect the E0 is exactly this, and the V should in fact become 4 times this, because by pulling out the dielectric, the electric field can actually increase. We're going to learn why that's the case in a second when we discuss the molecular ramifications of a dielectric. I've done the E, I've done the C, V0. So now the V0, whoa, Nelly. So now I can do the V0 is equal to K times V, which is 4.00 times 120 volts, which is equal to 480.0 volts. So we now have that. And the last thing I need is the new energy stored. So U0 is equal to 1/2 CV squared. That's going to be 1/2 times C, which is 1.77 times 10 to the negative 8 farads times 480 volts squared. So 0.5 times 1.77 e to the negative 8 times 480 squared. That's going to give me 2.039 times 10 to the negative 3 joules. And that's the new energy. Now notice with that one, the C went down by a factor of 4, and the V went down or went up by a factor of 4 squared. So we expect this new U should be up by a factor of 4. So if I divide that 2.039, if I divide that by 4, I should get the original potential energy, which is 5.097 times 10 to the negative 4th. And sure enough, that's exactly the number that I got in the previous part. Okay, any questions on that? If anybody thinks they can figure out what went wrong with that E being V over D, by all means turn it in. I'll give you extra credit. But right now, if I tried E is equal to V over D instead of paying any attention to the sigma over epsilon naught, ooh, I bet you that's the problem. E is equal to sigma over epsilon naught, but it also has a factor of K in it. That's the problem. So I want to say if that's the case, then 2400 or 2.4 times 10 to the 5th times 4 gives me the 96, which is this voltage down here. So I think that's really what happened. Yep, that's what it is. So now if I did the voltage, which is 120, divided by the distance, which is 2 e to the negative 3, that's going to give me 60 kilovolts per meter. That's not quite the same. So anyways, I do think that's what went wrong, but I think that's good enough for right now. You can look, there's an example just like this in your book, different numbers, but pretty much the same thing. So you can look at that. This actually shows you how to do it as well. Your book can show you another way, so that would work fine as well. I guess that's really the problem, because when I did V over D, yeah, that would work. Okay. So yeah, I'll just let that be, but you guys can try to track it down still. I've sort of given you a hint at what it is, and I'm pretty confident that's going to fix it. But what I'm going to do now is I'm going to talk to you about the molecular description of dielectrics. So what I'm going to do is I'm going to draw a parallel plate capacitor, sort of really big, if you will. And what I'm going to imagine is that parallel plate capacitor, I don't like that one, that parallel plate capacitor okay, there's one plate. Here's the other plate. What I'm going to imagine is this has a bunch of positive charges on this side, and this one has an equal number of negative charges on the other side. That's sort of the way we picture electric fields, as if they originate or start on a positive charge and end on a negative charge. So for instance, the electric field here is E. Okay. But now what we're going to do is we're going to look again, but this time we're going to put a dielectric in it. And something different is going to happen. And the thing that's different that's going to happen is with the dielectric in it, some of these electric field lines are going to have issues popping up. So let me draw you the dielectric, which I'll say is right here. Like that. So there's our dielectric. Again, I have the plus charge, plus charge, plus charge, plus charge, plus charge, plus charge, minus, minus. I didn't necessarily change the number for any reason other than the fact that I wanted you to see more lines. So you can imagine that the electric field still goes like that, but because the dielectric is made up of molecules and atoms, what's going to happen is the individual molecules and atoms are going to become polarized. And that's going to cause sort of a backwards electric field inside of the dielectric. So these are supposed to be the actual molecules or atoms in the dielectric. And what's going to happen is the positive charges are going to run away from the positive plate. So I'll get a negative over here and a plus here, negative plus, negative plus. And basically what that looks like is now our electric field line comes from here to here and then goes from here to here. And basically there's something equivalent to it as a electric field inside the dielectric ED. Then you're going to have another one that might, for instance, go all the way. But again, you've got this minus plus, minus plus, minus plus stuff in all of these. So that's what actually physically happens. So what we can do is we can say, for instance, that the electric field in the dielectric is equal to the electric field that it had when there was no dielectric, which I'm going to call this E0, okay, minus the electric field induced and actually, let me change that. I will say, there you go. I will say that this in here is what we call the induced electric field. So it really is the electric field that that happens within the dielectric or something like that. You can sort of think of it that way. Well, what we know is from the previous examples that when you plug a dielectric of constant K into a parallel plate capacitor, the electric field drops by a factor of K. So that means this is all going to be equal to E0 over K. So now if we look at just this part right here, all the way to there, then what we can see is that E0 times 1 minus 1 over K is actually equal to E induced. Okay. So what we have now is the induced electric field in the dielectric is equal to the original electric field times 1 minus 1 over K, but that also can be written as sigma induced is equal to sigma 0 times 1 minus 1 over k, or it also means that Q induced is equal to Q0 times 1 minus 1 over k. That's the main result that we're working out here. Okay. So we're going to do now another problem, and this should be the last one, and we'll be finished with chapter 24, which means I don't think I'm going to have enough time to get started into 25, but I definitely recommend you reading it next time. So what I'm going to do now is I'm going to share the screen with you, but I'm going to share my textbook screen. And this is the problem we're going to be working. I'm also going to pull up the chat window so you guys can look at it. So the last example we called example 5, so I'm going to call this example 6. And I'm going to say this is essentially example 24-14. So you can refer to it. It says a parallel plate capacitor has an area A equals 250, which I want to call 250.0 underscore square centimeters, and a separation D is equal to 2.00 millimeters. The capacitor is charged to a potential difference. V0 is equal to 150 volts. Then the battery is disconnected. Okay. Once the battery is disconnected, which means the charge doesn't change, so that says Q equals constant. Okay, and that's part of the lessons that I just wrote on the previous page. And a dielectric sheet of the same area but smaller thickness will be put in. So we also have K equals 3.50 inserted. And the thickness of the dielectric is going to be 1.00 millimeters. Okay. What we want to know is A, we want to know C0, and B, we want to know the charge on each plate. So I'm going to say Q0. And then C, it says the charge induced on each face of the dielectric. So we want to know Q induced. And then part D, we want to know the electric field in the dielectric. So we want to find out ED equals question mark. And then E, sorry about that. That's the electric field between the plate and the dielectric. So this is just regular E. Oops. So this is the E between the plate and the dielectric. This one is the electric field in the dielectric. That's what part E is about. And then part F, they want to know the potential difference between the plates. So V equals question mark. And then G, we want to know the capacitance. Okay, so that sounds a lot bigger and nastier than it really is. So don't fret it too much. I'm going to say solution. What we know is C is equal to epsilon 0 A over D, and we know that that would be C0, and we also know that C is equal to K epsilon 0 A over D. And I think that's pretty much good enough to get us started. So what we're looking at here is we first want to start off with part A, And part A, they're asking for the capacitance before it says capacitance, initial capacitance of the air-filled capacitor. So C0 is equal to epsilon 0 A over D, which is 8.85 times 10 to the negative 12th. I'm going to leave off the units here just for speed. In this case, that becomes particularly problematic because I had to convert that unit. So what I'm going to do is I'm going to say 100 centimeters in the bottom and 1 meter on the top. That's going to convert one of the centimeters squared to to meters. And then I'm going to do it again. And that'll convert the other one. So that takes care of that. And then I'm just going to put the distance in with the exponent instead of the millimeters. And this is going to be 2.00 times 10 to the negative third, like that. So this is the right, these are the right numbers. That should work out okay. So I'm going to say 8.85 e to the negative 12th times 250. Now here I'm going to say divided by parenthesis. I'm going to say 100 times 100. That takes care of the 200s to convert units, times 2e to the negative 3, close parentheses. This gives me 1.106 times 10 to the negative 10th farads. And that's equal to C. That's equal to C0, basically. Oops. So now I'll box it off. That's our first answer. Now, the second part, B, they want to know the charge. So remember, Q is equal to CV. So this is going to be Q0 is equal to C0 V0. So this is going to be 1.106 times 10 to the negative 10 farads times the voltage, which is 150.0 volts. Again, I'm doing that to make sure I have 3 sig figs. So times 150 gives me 1.659 times 10 to the negative 8 coulombs, and that's equal to Q0. Now I'll just look at those two answers on the book and see if I got the same results. They have 1.11 picofarads. That's the same thing I've got. A pico is 10 to the negative 12th. So I divide by 10, divide by 100, that would give me 10 to the negative 12th, and I multiply by 100, that would give me that would give me 110.6. So yeah, that exactly matches it. Now we need part C, which is the charge induced on each face of the dielectric. So with that one, we're going to use just C. Q induced is equal to Q0 times 1 minus 1 over K. That's going to be 1.659, which, by the way, I did check that. That's 1.66 times 10 to the negative 8. So that looks like we got it the same answer they did, times 10 to the negative 8 coulombs. Now I'm going to multiply that by 1 minus 1 over 3.50. So I'll do 1 minus 1 divided by 3.5. That gives me 0.71428. Now I'm going to multiply that by 1.659 e to the negative 8. And that gives me 1.185 times 10 to the negative 8 coulombs. And that's equal to Q induced. So that's the actual charge that's going to pop up on the face of the dielectric. And your book says it's 1.19 times 10 to the negative 8, so that makes me feel good. I know I got that right. Part D, the electric field in the space between each plate and the dielectric. This is the slightly trickier part, but the main thing is it's sigma over epsilon naught, which is the standard electric field when there's no dielectric present, which is the mistake I made earlier, don't forget. So E, oops. So for E, I'm going to say E0 is equal to sigma over epsilon naught. So that's going to be Q over A epsilon naught, like that. We know what Q is. Q is going to be the 1.66 times 10 to the negative 8. So that's 1.659 times 10 to the negative 8 coulombs divided by 250.0 over 10,000. That's what 100 times 100 is. And that'll be in meters squared, of course. And then epsilon 0 is 8.85 times 10 to the negative 12th coulombs squared per Newton meter squared again. Okay. So 1.659 e to the negative 8 divided by parenthesis, another parenthesis, 250 divided by 10,000. Close that parenthesis. Now I'm going to say times 8.85 e to the negative 12th. Close that parenthesis. And that's going to give me 7.498 times 10 to the 1, 2, 3, 4. And that comes out in volts per meter is equal to E0. That's essentially the same thing your book got. So again, I feel like I didn't make any arithmetic mistakes. So we can continue on. Part F. This is where they want to know the voltage. Now, what I remind you is that the voltage from one plate to the other is the negative integral of E dot dl. Okay. So because of that, we're going to get basically, oh, I forgot D. Oh, no, I did do D. So I forgot E. That's what it was. Okay. So this is part D. Sorry about this, everybody. We're almost done. Don't worry. There's D. There's F, but I need to do E before I do F. So let me finish that out. If you guys have to go, you're free to go, of course. I'm going to finish this up no matter what. So I'm going to do E next. And E is where we're asked for the electric field in the dielectric. So the electric field in the dielectric is supposed to be the electric field divided by K. So that's going to be 7.498 times 10 to the 4th volts per meter divided by 3.50, which is the dielectric constant. So I'm going to take this and divide it by 3.5, and that gives me 2.142 times 10 to the 1, 2, 3, 4, 10 to the 4th volts per meter, and that's equal to the electric field in the dielectric. Oops. So I'll box off this answer. And now the easy part, the two easy parts happen. So F, we have delta V is equal to the negative integral of E dot dl. That's what the voltage is. But in this case, it's the electric field is going to be constant in the space between the plate and the dielectric. And then it's going to be a different constant, but a constant again through the dielectric. And then back to the original electric field again in the first part for the space between the dielectric and the next plate. So all I have to do is say that it's going to be E0 times basically, let's say 1/2 of D minus L plus ED times L plus E0 times 1/2 D minus L. So you can see that that's going to work out to be E0 times D minus L plus ED times L. So the E0 we already found was 7.498 times 10 to the 4th volts per meter. Now I got to multiply that by D minus L, which is 2.00 minus 1.00 times 10 to the negative 3rd. I'm going to put this in parentheses, make that a square bracket, 10 to the negative 3rd meters, plus the other magnetic field or the other electric field, which is 2.142 times 10 to the 4th volts per meter times L, which is 1.00 times 10 to the negative 3rd meters. So basically what I'm going to get is 7.498 e to the 4th times 1 e to the negative 3. That gives me 74.98 volts per meter. And then the other term is 2.142 e to the 4th times 1 e to the negative 3. That gives me 21.42 volts per meter. So when I add these two together, 74.98 plus 21.42, I get 96.4. Oh, by the way, that's volts, not volts per meter. Sorry about that. The volts per meter, the meter part canceled out when I multiplied it by the L or the D minus L or all that good stuff. So that's why it's just volts. Sorry about that. And let me fix this here. So that's just volts. So the total answer is 96.40 volts. And that's equal to V. And now I'll box it off. And the last part, remember, the fundamental idea behind the capacitance is basically the charge divided by voltage. So now I can say for part G, which I meant to write in purple. So for part G, C is equal to Q over V. Well, that Q is the Q that's actually going to be on the plate. So that's actually going to be the 1.659 times 10 to the negative 8. Oops. Coulombs. And then I'm going to divide that by 96.40 volts. And that's going to be 1.659 e to the negative 8 divided by 96.4 gives me 1.721 times 10 to the negative 10th farads, which is equal to C. So notice it didn't come up to a full 3.5 times the original capacitance because it didn't fill the whole space, but it did come up. So that is basically it for chapter 24. We've completed the chapter, and I will be pushing back chapter 25 to at least next Sunday. But 24 should be due pretty soon. I'll double check the date on that, but you guys are free to go. And I know I've got one person here for questions, so I will ask, let anybody ask questions. I'm looking here. Someone asked me, did I get my text with a test question? And if so, could you answer it after class? Yeah, let me check that real quick. Benedict, I'm going to give the students that are in the section of the first priority, but then I'll answer you if that's cool. Let me check my text message. This is supposed to be from Ethan. I see one from another student that's not you. What's the last four? Can you type on the chat, Ethan? What's the last four digits of your phone number? Just type it on there, so don't say it out loud. We don't want it on the internet. Gotcha. Ah, okay, I see it. Oh, yes. Okay, I see your problem. I see the work that you turned in. And it says, I would say, Ethan, that your work on that lacks a little bit. What I would recommend you do to look at that is go back and let me actually let me go ahead and continue to share my screen. But what I'm going to do is I'm going to go back to modules. And now I'm going to go in your class to not this one. Ah, here you go. See this problem right here, flux and Gauss's law? That's what you need to look at to figure out how to do the electric field near an infinitely large plate. So it's the second example on that one. You can just do a search for infinite in my YouTube channel, and that'll bring you up some other examples of it. It'll bring up the infinite plane, it'll bring up the infinite line charge, and the infinite cylinder. But this one right here definitely has it, so you're welcome to check that out. But what you were doing just lacked some critical details.
Okay.
If you look at it and still don't get it, send me a text and I'll help you explain it a little bit, or help explain it to you a little bit easier. Okay.
All right. Thank you.
All right. Have a good one, Ethan. John, did you have a question, sir? Not sure John's still here. All right. I'm going to stop sharing my screen now. All right. So Benedict's here and has questions. John hasn't asked any questions yet. So I'm not even sure John's there because I asked him a question and didn't get a reply. So go ahead, Benedict. What can I help you with here? Oh, you are here, John. Sorry. Thank you. I thought that was you I heard a second ago, but I wasn't sure if it was you or Benedict. If you have a question, go ahead and ask me whenever you want. But Benedict, I'm going to answer his question real quick. And then if you have one, you can either, post a picture of it or ask me verbally or ask me by text through the chat. Go ahead, Benedict. What you got, bud?
Okay, so I got a few questions from the test that I got wrong that I would like to go over.
Okay, so this is regarding the test, that the face-to-face test or the online test or the practice test?
The face-to-face.
The face-to-face. Okay, so if you're doing the face-to-face, then I got to kill the recording because I don't want that going on the interwebs because we still have students that haven't taken it. But I'll go ahead and stop recording, and we can go ahead and field the questions. Actually, I don't want to do that. I want to just stop recording.